yet before he did his PhD in Italy, in Sicily, with Luciano Mazzola. Enrico is difficult to introduce because he's working at so many different things, ranging from alternative theories of gravity, possibly Bardeen theory, effective on body, orbits of point particles around curve. So he's worked on a lot of things over the years, and today he's telling us about another topic of his research, evolution of the strings of massive black holes.
Thank you for the introduction. So, first of all, I'll give you a brief outline of the talk. So, we start by explaining why black hole spins are important. So, I'll try to convince you that this is important. And to do so, we'll give you three examples of the physical effects of black hole spins. The first one being the so-called brain dragon. And review that both in isolated and binary black holes, and explain how brain dragons are dealing with gravitational wave and electromagnetic emission efficiency. And we'll then move to a second physical effect of the spin, which is the so-called Bardeen-Petterson effect. So we explain what that is and how that relates to gravitational wave first, and how it modulates gravitational wave. So it does have actually an observational effect. And finally, I will cover a third aspect of the third effect of spins, which is the production of jets in massive black holes and their effect on their host galaxies. So by this first part of the talk, I hope I will have convinced you that black hole spins are indeed important, and that it doesn't make sense to evolve to study the evolution of black hole spins separately from the evolution of their host galaxies. So in the second part of the talk, I will present some work that I did. And in particular, we will present a semi-analytical model for galaxy formation that I use to study the coevolution of black hole spins, or more general massive black holes, and the evolution of their host galaxies. So in particular, we'll focus on the evolution of the spins, and I will try to explore the implications of my model for gravitational wave detectors, and the gravitational wave detectors might easily decide what we get to test. So first of all, what are black holes? So for a relativist like me, black holes are very simple objects. So they're characterized by three quantities only. The mass, the spin, and the electric charge. So the electric charge, for most astrophysical purposes, is negligible, so we can safely set it to zero. And if we do so, the dynamics of black holes is only related to the two quantities, the mass and the spin. So the mass behaves like you would expect in Newtonian theory, at least at the lowest order. But the spin is a completely different kind of works. It's actually a genuinely relativistic effect, so we must be careful about how we handle it. So we try to give you a taste of what is the effect of the spin of black holes. So the first effect, which you're most likely familiar with, is the brain dragon. So its usual manifestation is the dependence of the location of the innermost stable circular orbital on the spin of the black hole. So as you know, the ISCO moves inwards as you increase the spin of the black hole. And this is not simply a geometrical effect, because it's actually related to the efficiency of the conversion between gravitational and electromagnetic emission in accretion disks. So what the brain dragon does is to increase the efficiency of emission of in accretion disks in a monotonic way with the spin of the black hole, and the efficiency can be as large as 40% in the case of the maximum spin of the black hole. And again, this is an effect which has wide astrophysical implication, because it can be tested actually with fitting method or radically alpha line, so it's actually a method to measure the spin of the black hole. So this you probably already know, but what is sometimes a little bit less known is that this brain dragon also acts in the binary black holes. And it goes under, known with a different name in binary black holes. It's sometimes called spinoric coupling by Postmotonian people with Postmotonian theory, or another effect by numerical lattice, but it's essentially the same thing. So if you have a binary with high spins aligned with the orthogonal momentum, so spins pointing in the positive z direction and angular momentum pointing in the positive z direction, the effective ISCO of the system moves to small radii, so the binary, the black hole binary describes a lot more for plunging and eventually emerging. Whereas if you're in configuration which has spins pointing in the negative z direction and the angular momentum pointing up, what you have is that the effective ISCO is a large radii, and the binary only describes few orbits for plunging and emerging. These are actually numerical simulations of black hole binaries. So this is actually the same effect as you would have in an isolated black hole. And in the same way as in an isolated black hole, the frame dragging is related to the electromagnetic efficiency. In the case of a binary black hole, the frame dragging is related to the efficiency of gravitational radiation. So you know, if you have a binary black hole, binary black holes, the final mass of the system when the two black holes have merged is less than the initial mass of the system because you will have emitted some mass in gravitational waves. And the final mass decreases as you increase the spin of the black holes involved in binary. So these are actually micro simulations for equal mass black holes with equal spins and spin parameter A for each one of them. So as you see, when the two black holes have maximum spins, they can emit as much as about 12–13% energy in gravitational waves. So this is another effect of the frame dragging, which is testable with gravitational wave detectors. So the second effect that I want to review in this first part of the talk is the so-called Bardeen-Petterson effect. This is an effect which was started back in the 70s by Bardeen-Petterson. And it's actually amounts to essentially the interaction between the frame dragging, or the spin-orbit coupling, and dissipation, the viscosity of an accretion. So that's what if you have a black hole with spin in a certain direction, if you have an equatorial disk around the black hole, at large distance from the black hole, the inner part of the accretion cone gets essentially worked by the combined effect of the velocity and the spin-orbit coupling, and it aligns with the equatorial near the horizon of the black hole. So this on the viscosity time scale, essentially, and on a longer time scale, about 75 years for massive black holes, this work disk exerts force on the spin of the black hole and essentially aligns the spin of the black hole with the larger scale accretion disk. So why is this important? The reason why I want to stress this is that because in a galactic environment, if you expect mergers of massive black holes to happen in the presence of certain nuclear disks, which are formed in the case of major mergers of galaxies, for instance, as we explained later. So you expect mergers of massive black holes to happen in a gas-rich environment. So you expect certain nuclear disks that are expected to align the spins of the two black holes. So if you have a binary in a gas-rich environment, the spins of the two black holes get aligned with the particle angular momentum of the certain binary disk, and by the time the binary merges, you have aligned spins if you're in a gas-rich environment. On the other hand, if you're in a gas-poor environment, in which you don't have much gas in the center, the spins of the black holes are not aligned by the Bardeen-Petterson effect because you don't have any gas, and they're essentially randomly oriented. In which case, you have other relativistic effects, which are so-called precession effects. So if you have a binary with randomly oriented spins, the spins in general precess around the total angular momentum of the system because of the spin-orbit coupling, and this causes observable modulations in the gravitational waves. So if you have spins which are randomly oriented, the spins rotate around the total angular momentum of the system, and they cause these modulations in the gravitational wave force, which are actually which would be visible with gravitational wave detectors. So another way in which the spin of black holes can be constrained using observations. And so, as I said in the introduction, however, this talk would be about the co-evolution of black hole spins and the galactic hosts of the black hole. And all the effects I've talked about so far happen on very small scales. Because if you have a massive black hole, like 10 to the 6, 27-story masses, the size of the horizon of the black hole is of sub-parsec scale, 10 to the -6, 10 to the -7 parsecs. So this scale on which the effects of the spin are visible is much smaller compared to the other scales which are involved in galactic evolution. So if you have a massive black hole accretion disk, of course you have a parsec scale size. If you have a certain nuclear or certain binary disk, this can be of 100 parsec scale. The galactic spheroid is about parsec scale. The galactic disk 10 parsec scale, and you get up to parsec scale for the halos. So it seems that the black hole is very tiny compared to the other scales involved. So you wouldn't expect much effect from the spin of the black hole on galactic scales. However, there is a third effect that I want to talk about, which will go into the main part of this talk, which is the production of jets. So we know that massive black holes in AGNs produce jets that reach high into the galaxy. This is, for instance, a picture of M87, and you see the AGN in the center, and then you see a jet in one direction, and probably the remnant of the jet in the other direction. And this is commonly thought to be very important for galaxy formation because what we expect is that the kinetic energy of these jets is transferred to the galaxy and hits the galaxy essentially out. So if you transfer the kinetic energy of this jet to the gas of the galaxy, essentially hit the galaxy up and different star formation. This is known as AGN effect. So before explaining more in detail why we think the AGN feedback is important, let me say that we have a pretty good understanding of how jets are formed around black holes. So the original piece of work in this respect dates back to Glassberg's in 1977, and these authors showed that jets can be produced around spinning black holes if they are immersed in an external magnetic field, which is thought to be anchored, for instance, by the thin accretion disk or by a certain movement disk. And the reason why these jets are produced is that if you have a spinning black hole, you have an ergo region near the black hole, and so the magnetic field lines essentially must correlate with the black hole horizon inside the ergo region. And it is this movement of the magnetic field lines inside the ergo region which causes the production of jets. Now, more recently, Carlos Valenzuela, unfortunately is not here, and collaborators have shown that you don't really need a spin to produce jets, but you can produce a jet even if you move a non-spinning black hole in an external magnetic field, essentially because the magnetic field lines of the black hole are, the magnetic field lines of the external magnetic field are attracted by the moving black hole. And more importantly, Valenzuela and Giglin show that this jet production is also present when you have a binary system of black holes in an external magnetic field. So they have actually numerical simulations for this. So you see the two black holes moving in an external magnetic field, and you have jet production from each single individual black hole. And then when the two black holes merge, you end up with a single jet. But what is important is that this jet produced during the merger is amplified by the strong field effects that happen during the merger. So it's much more powerful than a traditional transfer-like jet.
So where does the external magnetic field come?
From the circumbinary disk. So we don't really know the strength of the magnetic field. The one important thing is that the power of this jet scales, I think, quadratically with the strength of the magnetic field, and we don't have a very good understanding of how strong the magnetic field is in the environment of the galaxy. So this is just to say that we have nowadays a good understanding of the jet production by isolated and binary black holes. And so why do we think these jets are important in the galactic environment? So the reason is the so-called cosmic null-sizing problem. So we know that the formation of dark matter halos is essentially the bottom-up process. You start with small dark matter halos at high redshift, and when time goes by, the dark matter halos merge, so you end up with larger structures at z equals 0. On the other hand, if we look at galaxies in the sky today, and we look at the most massive stellar systems, we see that the most massive galaxies have the oldest star populations, and they vary in their formation. So it seems like the formation of the baryonic structures in galaxies happens on top-down fashion. So it seems like it's more. It seems like the biggest systems are formed first, and the smaller systems are formed later. So this seems to be contradiction with respect to the bottom-up formation of dark matter. So the way this discrepancy is resolved in our current understanding of galaxy formation is by means of BHN filter, because if you have a very large system, a very large dark matter halo, you have, because of the Lagrangian relation, a very big black hole, a very strong jet, so you quench transformation earlier than in a small system. So the BHN filter is essential to ensure that in large mass systems, star formation is shut down earlier than in small mass systems, and therefore solve the cosmic lifestyles of problem. So on the one hand, this tells us that it doesn't make sense to study the evolution of black holes and the evolution of their host galaxies in a separate way, because we know that the evolution of black holes depends on the amount of gas that is present in galactic nuclei, and that is related to how the galaxy works. On the other hand, the black hole, because of the BHN filter, must react on the structure of the galaxy by means of the jets, and we know that this effect must be important if we want to make sense of the cosmic concepts. So, in principle, we could address this problem of the coevolution of black holes and galaxy formation in a completely numerical way. So you could have a hydrodynamical simulation or an MBH simulation studying the formation of black holes and galaxies. However, this is in practice not feasible because you have a range of scales which go from the sub-parsec scale of the massive black hole up to the megaparsec scales of the dark matter halo. So and also you have complicated nonlinear visibility processes on small scales that you need to resolve. So although there are some numerical simulations, what I used in my work is a counter approach, if you want. So I try to construct a semi-analytical galaxy formation model, which I will describe now, and which includes a number of components. So it includes dark matter halos. It includes a hot gas component, which is essentially the intergalactic medium. It includes cold gas, the cold gas phase, which I distinguish in both bulges and disks. It includes a stellar phase, which again I distinguish in spheroidal components and disk components. It includes finally the circumnuclear disk around the black hole, the massive black hole accretion disk, and finally, of course, the massive black hole, which is the one I really want to study. So we'll now go very quickly through each one of these components, and I'm trying to go quite fast, but if you have questions, just stop me. And we'll be happy to answer any questions or anything that is not clear. So for the dark matter, I essentially use an extended press reactor formalism. So for those of you who are not familiar with extended press reactor MBHs, they're essentially based on the fact that the perturbations of the density field laid down by inflations are Gaussian. And the evolution of this density perturbation is started with linear theory, linear perturbation theory, corrected with a spherical Barausse model, Barausse model. So I use extended pressure numerical fields modified to reproduce the results essentially of the independent graph, which are dependent on the simulations of the dark matter. So basically what I have are, for each dark matter halo at z equals 0, I have all its history of the earlier times. So I start with small dark matter halos at high redshift, and with time these dark matter halos merge, and they also create dark matter from their surroundings. So they merge, and finally you get with one dark matter halos or halo at z equals 0. And for each one of these dark matter halos, I assume an invariant density profile, which is again the density profile which is drawn from numerical, from analogous equations. So this is pretty much it for the dark matter sector. Then on top of this dark matter skeleton, I have a hot gas phase, which has primordial metallicity. So it's essentially a process gas, which is brought in by the dark matter accreting onto the system. So the accretion rate, if you want, for the hot gas phase is proportional to the accretion rate for dark matter through this binary fraction of F, which includes the effect of the ionizing background with the first phasers and population of stars at high redshifts. And I assume that this hot gas is the Wiener temperature of the halo, unless you're in a regime in which all the accretion flows are important. So the polar accretion floater essentially means essentially low mass halos of high redshift. People think that the across the IGN streams in on a dynamical time scale, and it is not shock free to the bigger temperature. Anyway, this is my own. So I have a hot gas phase on top of my dark matter halo, and this hot gas phase collapses into gaseous disk components on a dynamical time scale if the cooling of this hot gas phase is very efficient, or on the cooling time scale if the gas cools very slowly. So essentially you have a hot gas phase, and this hot gas phase collapses or cools down into galactic disk. So for this galactic disk, I assume an exponential density profile with scale radius calculated by essentially conserving the angular momentum mass of the collapsing hot gas. I assume star formation in this galactic disk, and I take from the literature the best recipes for star formation in galactic disks. In particular, I assume that the star formation rate is proportional to the fraction in molecular clouds, because we know that star formation happens in molecular clouds. And this recipe essentially reduced with the Schmidt-Kenkat law in high density environments. So because I have star formation in these galactic disks, I also have a fraction of my forming stars are given by supernovae. And these supernovae, they explode in short time scale compared to the time scales of the that I'm looking at. So I take into account the feedback, supernova feedback on the star formation. So essentially when the supernova explodes, it transfers some kinetic energy to the cold gas phase, and essentially it expels gas from the system. So the way I do essentially the supernova feedback is by comparing the kinetic energy emitted by the supernova explosion to the binding energy of the galactic phase. And then, so because I have star formation, we'll end up with a stellar disk, which I assume again to be given by an exponential density profile. And more importantly, both stellar and gaseous disks can develop bar instabilities when they become self-rotating. We know this from numerical simulations, and this is called the channel by which galactic disks can originate spheroidal components. So essentially, when I have a criterion in order to check when a galactic disk becomes self-rotating, when it does, I assume the disk is disrupted in a dynamical time and forms a spheroidal component. So for the spheroidal component, well, they can form from bar instabilities of the galactic disk, so as I explained why they can also come from major mergers, but very briefly I assume a certain density profile for the galactic bulges, in particular I have this density profile. I assume star formation in the galactic bulges as well, and I assume star formation is much more efficient in disks, sorry, in bulges than in disks, because this is something that we observe in the bulge. And I also include the effect of supernova feedback in the spheroidal component in the same way as I do in disks. So far I've essentially explained, I went through all the components which make a galaxy, an isolated galaxy. So dark matter, hot gas, galactic disks, and spheroidal components. However, in my model, the galaxies also merge. So when two dark matter halos merge in my merger tree, I also assume the baryonic structures inside the galaxies merge with a certain delay. Because when two dark matter halos merge, the baryonic structures in the galaxy don't merge right away, but they start circling one around the other, and they're brought together slowly by dynamic friction essentially on a giga-year time scale. So I include this effect. And during this dynamic friction time, I also include effects of tidal effects like tidal scaling and tidal evaporation that essentially reduce the mass of the satellite galaxy. So when finally the two galaxies, the two baryonic components merge, I distinguish between major mergers in which the baryonic components, the masses of the baryonic components of the galaxies are comparable, in which case I assume the stellar disks are disrupted. So major mergers disrupt the gaseous and stellar disks and form spheroids. This is again one thing that we notice in MBH and maximum observations. Whereas if I have a minor merger, I assume that the structure of the galaxy doesn't change, so the galactic disks survive. So this is essentially it for the galactic part of my model. So now I have to include the black holes in this picture. So if I want to include black holes, I need to assume a certain seed from which the black holes grow. Because if I start with no black holes, which I cannot, black holes don't grow at all if I start with mass. So I assume galaxies are populated by black hole seeds originating from population of free stars at z equals 15 or 20. And this is what I call the light seed model. Or I assume a different scenario in which black hole seeds form at lower redshift z equals 10, 15 from the collapse of protogalactic disks. And these black hole seeds have a larger mass than the light solar masses. And then, because I want to study the evolution of the spins of black holes, I also need to assign a spin to these black hole seeds. So I assign essentially a random distributed spin for these black hole seeds. And the final results for the spin evolution of the massive black hole population will not be very sensitive to this assumption, because as long as the black hole accretes a little bit of mass, it loses memory of the initial spin. So the black holes can then accrete gas into two phases, a quasar phase and the radium phase. So I include both these phases. Yes.
So when you said there's a delay that you have with applicant converge, but you always assume that the black hole seed comes in at the same time as the baryonic component?
Well, the black holes, I would mean if I make the black holes merge at the same time as the baryonic components.
Yeah.
Yeah, I do that.
Okay.
And this is something. Yeah, so there could be, the thing is the dynamic friction and scale of galaxies over the giga year, and it could be, and it has many uncertainties. So in principle, I could include an extra delay, which would probably be another giga year, which would be the delay between the merger of the baryonic components and the merger of the black holes. But yeah, that is a possibility. This is my work, but I don't think the results will be very much effective. We can discuss this later. So I have two accretion phases for the black hole, a quasar accretion phase. So I assume that when star formation happens in the spheroid, radiation directs from the newly formed stars pours cold gas into a circumnuclear reservoir, which then accretes onto the massive black hole with a certain on a certain time scale, the accretion, which is a free parameter of my model. So I have star formation in the bulge. This forms a circumnuclear disk, and this circumnuclear disk originates a parsec scale accretion disk, which then heats the black hole. And an important thing is that I assume that this quasar-phase accretion is a thin disk accretion in a gas-rich environment. So if I have a lot of gas in the galactic center, so if the mass of this circumnuclear reservoir is much larger than the mass of the black hole, I assume coherent accretion for the massive black hole. Whereas if I'm in a gas-poor scenario, I assume chaotic accretion, meaning that I assume that accretion by the black hole happens by essentially the black hole eating clouds with random distribution of the orbit random away. So this is, well, maybe some of you will not agree with this, but this is essentially what people think, because we know that the quasar phase must be thin disk accretion, as we want to explain, because we know that quasars have certain luminosity function. So from that we know that the efficiency of accretion must be compatible with thin disk accretion.
So it depends on the radius that you're starting from, whether this is a reasonable conclusion.
Well, you mean the fragmentation, transformation, and this becomes saturated?
No, I mean, it's the gas is collisional, so an accretion disk can certainly form into a much less massive gas than a black hole.
Yeah, of course, yeah. So you mean even in this situation you can have thin disk accretion?
Well, the division between the massive reservoir bigger or smaller than the black hole is somewhat.
That's what the state of this certain minor reservoir they consider as not 100 parsec.
When you think about it, the large scale gases, spiral galaxies.
Yeah, I mean,
settle into some nearly planar configuration.
Yeah, that's very true. Anyway, the reason why I do this is there are SPH simulations which include which they find something similar, but I agree this is something that actually affects my results in a very strong way, and we can discuss this.
Does it matter, because you're trying to figure out what the spin is of the black hole?
Yeah, it matters a lot. Yeah, this is something.
Does it matter if it's a thin disk or a thick disk?
Well, I mean, what matters is if you have matter accreting coherently on the black hole with a fixed direction of the orbital momentum. Because essentially what happens is that if you have coherent accretion,
Did you get coherent thick disk
or well, in that case, the additions, well, qualitatively the results will not change. So it depends on yeah. So basically, if you have coherent accretion, the spin evolution is going to, orbital momentum and the energy of the inner edge of the disk. So if you have thick disk accretion, the inner edge will change a little bit, but it will not, let's see, it will have a spin out with coherent accretion. On the other hand, if you have ionic accretion, matter comes into the black hole with essentially random distribution of the direction of the orbital momentum, and because retrograde orbits have a larger impact cross-section, black hole retrograde orbits have a larger cross-section, ionic accretion then causes the spin of the black hole to decrease. So this is the real decomposition. There's no real negative use.
I think you should remember that the merger of two galaxies with the slope points was not gas, but it was spheroidal component. That slope has some dimension. And certainly by the standard of the black hole and its local radius of influence, it has a lot of it. So there is, even in that case, some large-scale well-defined axis being I would think.
Yeah, I would think that as well. But since to see that, well, I have a thing is my model is the same as the model, so I need a simple recipe. So I'm not sure how I could, one would need an recipe.
Well, no doubt you were seeing some things in simulations that were guiding what you were choosing for your mathematical model. But I mean, you should keep in mind that
No, I agree. The reason why I was choosing for two regimes for accretion, I think similar words to my belief on similar classification model. People use either coherent, always a coherent accretion feature or ionic accretion feature. So to me, it seems more likely that during a dust form environment, you can discuss what the dust form means. You might have accretion by molecular clouds in the black hole, not necessarily the affinities or coherent accretion.
Yeah, but I mean, you're right. Let me go back to this spheroidal, galaxy case. I mean, yes. I mean, there are individual solar orbits with wide range of angular momentum. Nonetheless, there is some collective statistical average that would mean that you consider many clouds. I think you would still get.
Oh,
you reduce by a numerical factor. Yeah, you would reduce by a numerical factor the magnitude of angular momentum, but you do not get rid of the mean angular momentum.
I agree. Makes sense. So you push the matter to further direction, but still, I think people have spin on that would be a small effect compared to. Well, one should explain.
See, the point is that, of course, the angular momentum of stuff, any stuff coming in, can be much larger per gram than stuff that actually reaches the ischia. Right? So what matters, as I understand your approach, is what the orientation is, right? And so the issue is that there is, on average, some well-defined orientation. There may be a wide dispersion about that average, but there's still. So you're, you many events. I'm not sure you do. Are in a qualitative definition.
That's something that we check next one. Well, the second regime in which black hole can accrete is the so-called radial mode accretion, in which the black hole essentially accretes from the hot mass phase directly from the IGN. And this is well, this is thought to be important because, well, you think this accretion is not spherical, so because one accretion is actually spherical. So you expect the radial mode accretion mode to be essentially an direction-dominated accretion flow. So white has very low luminosity compared to the thin disk accretion, or the effect on the screen is small because the mode accretion rate is small. This radial mode accretion mode can have a very strong impact on the structure of the galaxy, because what we see in the simulation is that jets produced by attraction-dominated accretion flows, so radial mode accretion in my scenario, are much more powerful than jets produced in thin disks or in the quasar mode accretion mode. So what I do in my model, I go and take these peak informations which come from hydrodynamic simulations, which give me power of the jet produced by a black hole having a certain spin, and with an accretion disk which is either in the radial mode case or thin disk in the quasar case. And as you see, the normalization of the jet power is much larger for an attraction-dominated accretion flow than for thin disk accretion flow. So the radial mode, although it has little impact on the mass and spin inclusion of the black hole, can have a much stronger impact on the overall mass. And then I consider the feedback of this jet onto the galactic structure using very simple recipes. Well, so this concludes essentially my model for the galactic component. This is a very standard component for the galaxy formation. So this is essentially a state-of-the-art semi-analytical galaxy formation model. On top of this, I want also to study the evolution of black holes. So when two black holes merge, I calculate the mass of the final black hole remnant, the spin of the black hole remnant, and the peak velocity of the black hole remnant, essentially utilizing numerical relativity simulation. So I take essentially fitting formulas to numerical relativity results. And however, what you note is that the results of this formula depend very much on the orientation of the spins of the black hole. In particular, this one, the peak velocity, which is essentially the peak imparted to the final black hole remnant by the gravitational wave emission, which is not isotropic in general, depend very much on the orientation of the spins of the black holes. So what I do in my model, I check whether I'm in a gas-rich or gas-poor environment by comparing the mass of the circumnuclear reservoir to the mass of the black hole binary. And if I'm in a gas-rich environment, I know that the Bardeen-Petterson effect must somehow align the spins of the two black holes. Whereas if I'm in a gas-poor environment, so-called dry merger, I know that the spins of the two black holes must be aligned with the modulo post-nuclear effect. In general, they have a known zero angle. And so, in this, and using this information, I can calculate what the final mass, final spin, and the peak velocity of the black hole remnant is. And so, if you have misaligned spins, what you see from numerical relativity simulation, that you can have a peak velocity of up to 5,000 kilometers per second, the so-called superpeak configuration. And this is equal enough to reject the black hole remnant from the host galaxy. So each step, each merge, I calculate the peak velocity and compare to the escape velocity of the galaxy and see whether the black hole is ejected or is retained by the galaxy. So I'm going to go, I'll go very quickly through the calibration of the model. So my model has 4 parameters. So I have a parameter describing the efficiency of the supernova feedback, essentially how efficiently the supernova kinetic energy is transferred to the galaxy. This goes between 0 and 1. I have a model which parameterizes the power of the jets because we don't know much about the magnetic field in the galactic center. So and the jet power depends quadratically on the magnetic field. So I have this spot factor or the unity that I use to calibrate the strength of the agent feedback. I have this pre-parameter regulating essentially the strength of the radiation ray, which forms circumnuclear reservoirs. And I have a time scale on which the circumnuclear reservoir essentially forms the subparsic, parsic scale accretion disk of the black hole. So these are only 4 free parameters which I calibrate with a suite of cosmological observables. So I take a bunch of observables of z equals 0, so stellar mass function, baryonic mass function, the gas fraction, the star formation rate of z equals 0, the black hole mass function, some information on the morphology of galaxies, the scaling relations for the black hole, the F sigma, and the orientation. I have observables at d larger than 0, essentially with laser volumetric luminosity and star formation is a function of redshift. And this way I'm able to essentially calibrate the 4 free parameters from the model. And so when I want to use this model, I study the evolution of the spins of the massive black holes. So this plot is essentially a picture, an instantaneous picture of the spin distribution, the mass distribution of massive black holes at z equals 7. So in the, for example, axis has the mass of the black hole, in the y-axis we have the spin of the black hole, and the color code represents essentially the black holes in that mass and spin field. So I have both a light seed and heavy seed scenario. So the seeds correspond to this, when the light seed scenario, the seeds have 150 solar masses, so this line here is simply the seeds, the black hole seeds. This line here are the black hole seeds in the heavy seed scenario. But as you see, when you move away from the seed black holes, you see that the spin distribution is skewed towards high spins, essentially because you have a lot of gas in galactic centers, and this gas accretes coherently onto the black hole. And mergers between black holes happen on in gas-rich environments, so that the linkage aligns the spins of the black hole. So the spins are always aligned, either with themselves in a binary or with the original movement of this, and the spin of the black hole is skewed towards high redshift. And as you increase time, this tendency becomes more and more pronounced. But then at some point at z equals 4, you start seeing the bimodal distribution. You start seeing a bunch of black holes which have spin about 0.2. And this is because the black holes sterilize their host galaxy due to the AGN feedback, so they tend to be in a gas poor environment, so they accrete rather chaotically, and mergers happen between black holes in gas dry environments, in which the linkage effect is not important. So when you have random orientations of the black hole spins, or random orientation of the orbital momentum accretion disk, you start seeing the black holes tend to be spun down, so you start seeing a population at the z equals spin parameter about 0.1 essentially. And this has become more and more pronounced as you decrease the redshift. And at z equals 0, the prediction of my model is essentially that you have many black holes at spin 0.1, and a bunch of black holes with larger spin due to essentially the mergers. So now you, well, some people think this is not. So there are ways you can test this, of course. So one way is to measure the black hole spins with LIGO K alpha lines. So nowadays we have only a bunch of sources in which you can measure black hole spin with massive black holes with LIGO K alpha lines. However, the effect of systematics is very uncertain. In fact, well, the early measurements seem to point at very large spins for black holes into the systems, but well, there are other things which, starting from the same data, they get much smaller spins. So probably the final word on this will be given by future X-ray missions, such as Athena, which would hopefully be one of the mission of the European Space Agency, which should fly in the 2020s, which will allow much higher resolution spectra in the iron K alpha region, and will allow to measure spins up to z equals 0.3. However, I want to point out that any measurements coming from the electromagnetic field will have problems due to systematics, and also to some selection bias, because if you, because we know that high spins have much higher disk luminosity, because the efficiency is larger for accretion disks around 5 spin black holes. So these kind of measurements will always be biased towards high spins. So this is not really a way to, well, this is only partially a way to test my model. The other way is, of course, gravitational waves. So today, gravitational wave detectors will be able to measure the mass and spin of black holes within 0.1%. Actually, the mass within 0.1% and the spin within 1%. And they will also be able to tell the difference between binaries with precession spins and binaries with aligned spins because of the manipulations induced into the gravitational waveforms by precession. So today we have a bunch of ground-based gravitational wave detectors, but they're only sensitive to stellar mass black holes. However, in the future, we will have gravitational wave detectors such as the Einstein telescope, which essentially will be sensitive to intermediate mass black holes up to very high redshift. And hopefully we will have ELISA, again another initial concept of the European Space Agency, which should be sensitive to massive black hole binaries up to redshift equals 10. And maybe in further future we will have other detectors such as the CITA and the which will be sensitive to both intermediate mass black holes and massive black holes up to fantastic redshift. So whenever I predicted in this, my model could be falsified with future gravitational wave detectors.
Did you see any difference between the simulations in which you assume light speed?
Yeah, so for the spin evolution, and not qualitative. No. Yeah, so the final endpoint, which you might agree or not, the final endpoint is so when you check the black holes for mass more than 10 to the plus or mass in the simulation. What is different between the two models are the number of event rates for future gravitational detectors. So here you see essentially the number of mergers between black holes per year of observation as a function of redshift for light seeds here and for heavy seeds here. So and there are different mass ranges. So the red line is binaries with in which the total mass of the binary is less than 10 to the 4 solar masses. The blue line is total mass between 10 to the 4 and 26 solar masses. And the green line is binary mass more than 10 to the 6 solar masses. So essentially, so I chose these mass beams because the red lines are the sources for the Einstein telescope, so they're essentially intermediate mass black holes. And the blue and green lines are essentially sources for LISA. And whereas detectors like the CITA will be sensitive to all three mass ranges. So this is the light seed scenario. So you see a lot of events for essentially for the Einstein telescope up to 100 per year because you have light seeds. So these light seeds they emerge and they're essentially intermediate mass black holes. So you see a very strong event rate for the Einstein telescope. Whereas for the ELISA, so these events of course are not possible in the heavy seed scenario because you have seeds of 10 to the 5 solar masses which are completely outside the frequency range of the Einstein telescope. However, in the heavy seed scenario, you have 100 of events per year for these. So the way to test the different scenarios for the seeds is essentially by checking how many event rates you have with these. So the future gravitational wave detector will be able to tell you which seed scenario you have. So if you have only, with LISA you have only a few events per year, you're most likely in a light seed scenario, whereas if you have hundreds of events per year, you're in a heavy seed scenario. So this is nice, but also another way in which gravitational wave detectors can test my predictions is by checking how many precessing binaries or aligned spin binaries you would see with gravitational wave detectors. So as I said, in my model, I have a way to, relatable in one way, but still a way to understand whether binaries have aligned spins due to the Bardeen-Petterson or precessing spins in the case of current environments. So I plotted here the collection of wet mergers, of gas-rich mergers as a function of redshift in the three event rate, the three gas ranges that I introduced before. So as you can see, in general, at high redshift, we have a lot of events in gas-rich environments. So in these scenarios, you expect the spins of the black holes to be aligned with the Barausse effect. And as you increase cosmic time, you see many more marriages happening in accretion environments, essentially because the AGN feedback sterilizes the galaxy, so it makes the galaxy possible. So this is another way in which essentially any future gravitational detector can test this feature. So so another thing I can test with my model, or I can predict with my model are the mass ratios of the massive black hole binaries, which will be observed in LISA. So at higher redshift, in general, you will have comparable mass black hole binaries, and at lower redshift, you will have a smaller mass ratio binaries. And again, LISA will be able to test this prediction because we could measure the masses of black holes up to an accuracy of 0.1%. So I think I'll stop here. So just to conclude, so I essentially built a model which allows me to study the evolution of the masses and spins of supermassive black holes. Actually, the co-evolution corresponds to the evolution of the host galaxy by taking into account both the gas which the galaxy makes available to black holes to grow and the feedback of the black hole on the larger structure of the galaxy. So in 2 words, the prediction of my model is that you should have high spins and gas-rich mergers of black holes at redshift more than 3, whereas at lower redshift, you should have a prevalence of low spins and higher mergers. Simply because at low redshift, the gas is essentially sterilized by the AGN. And also what I find with my model is that LISA or emission similar to it will be able to test this picture and should see at least a few events per year in the light six scenario, or up to 100 events per year in the heavy six scenario. And it will also be able to test this model directly by having what fraction of the black hole binaries have precessing or non-precessing spins. So future work, besides improving the galaxy formation part in this work, is to include to calculate more precise event rates for LISA by taking into account the spin effects in the gravitational waveforms. And I have you can do that in different ways, but I have the model which I think is very suitable for that. And another piece of work, another possible development of this work is to study how different models for galaxy formation can affect my result and how gravitational wave detectors can have testing galaxy formation theory. And yeah, this is pretty much it. Happy to answer any questions.
My recollection is that Bardeen-Petterson et al. Had a Bardeen-Petterson et al. That they had a larger spin distribution, or higher spin.
Yeah,
they why what is it?
Yeah, they actually have 2 spin distributions. They consider either always coherent accretion or baryonic accretion.
Okay.
So they have a
coherent with the high one.
Yeah, coherent with the high one. They also have an optimal accretion which they have first take those spins.
Yeah.
So and also they always consider they always consider randomly aligned spins as varieties. And this is another thing very cool. I'm trying to improve on their model.
Another question is, so in the end, do you check to make sure you get the soul tabulation right? You know what I mean?
Well, I check.
Well, I guess one question is, because the efficiency that comes out of there is something like a little, like 15%, but there's, big difference.
Well, I didn't calculate the efficiency. Like what I did, I compared to the volumetric luminosity phasers, this function redshift. These are data from Hopkins in 2007, and I still have some discrepancy at high redshift. But still, the normalization is okay.
But do you get the right mass in black holes?
Yeah, when I check the.
Well, then I guess you must get some tabulation.
Yeah.
You get both those right.
Yeah, I checked that I have the correct massive black hole mass function at equals 0. So this is the massive black hole mass function at equals 0. And, yeah, I'm still a little bit low. Maybe massive.
When I have a accretion disk with misaligned black hole spin and then misalignment radius, if there's this misalignment angular momentum, what fraction goes out, what fraction goes into the black hole?
Well, the thing is, if you have a water accretion disk on the time scale, sorry, the bulges aligns with the black hole.
Well, no, the stuff is pouring in, so there's a radius of which, the outer disk doesn't.
Yeah, also, yeah. But if you want the work radius, which is what this picture, it's of a few gravitational radius, it's a spin arc effect.
Yeah, I know. But what fraction of the angular momentum? So
what fraction of the
outer disk has a different angular momentum than the black hole, and so there's a misalignment.
Oh, yeah. So you want.
And at that alignment radius, you have a characteristic angular momentum. So what fraction of the delta L goes out, diffuses out, and goes into the black hole? What's the fraction type of quantify that?
I don't even remember. I know again. The work radius is like 40. This case is like actually 20 degrees later. I'm not sure how much.
Depends on the viscosity.
In this solution, what fraction of the black hole that is out of the galaxy can you compare that to?
Yeah. How many black holes are kicked out?
We have a lot of dry motions, right? It's more like
Well, many of them. Well, this is how many black holes are ejected from the galaxy.
yeah. How many galaxies will end up without a black hole?
I'm sorry.
How many galaxies will end up without a black hole at the end?
Oh, how many? Well, it's a good question. I still get the black hole mass function right. So not many galaxies will have I haven't checked the fraction, but I still get the correct black hole mass function. The thing is, even though many black holes, so I find that many black holes are ejected from the galaxy, but it doesn't prevent the final galaxy to have a black hole. If you start, suppose you have a very high ejection probability of black hole. Suppose you start with a black hole in each galaxy. So suppose you have a first merger situation in which most galaxies have their black hole ejected. So suppose in only one galaxy you still have a black hole. That black hole will survive until the end, because there will be no other black holes to merge with. So this is something which is known. So even if you have a very high ejection probability, very few galaxies that Z equals 0 will be devoid.
Are most of the dry mergers in your solution that go with it?
Yeah. Yeah, but low redshift you have bigger galaxies. You have bigger galaxies, so the escape velocity is
Good. Those don't get it.
yeah. In fact, if you check the ejection, I have the ejection fraction of black holes. Sorry, this is yeah, so this is the ejection rate of black holes. So in the lower mass beam, the red line is binaries with less than 10 to the 4 solar mass. You have many black holes which are ejected, but that's simply because they're small black holes that haven't grown, so in their galaxies there is very little gas, so there is very little baryonic structure to keep them in the galaxy. But if you go to mass ranges of more than 10 to the 4 solar mass, you see that only Z equals 10% of the black holes are ejected. So very few galaxies.
So along those lines, what about galaxies where the black hole will be offset from the center for a while after and additionally where you're going to take in
that's something, yeah. But then I should, if I really want to do that, I should be more realistic, because now I assume that whenever, so I have, when the dark matter halos form, I assume the galaxies essentially, so I have post galaxy in the center and the satellite galaxy that rotates around the region, and that's very nearby. When the two galaxies merge, they exchange the black holes merging, which is not really good, especially for the effect of the gas reaching environment should include the merge of the black holes will be delayed, essentially where the viscosity times stable, and the prime mergers have to take into account the distributions that are less than most common arrangement. That's something I want to do, but I need to modify that.
So you assume it would go to the center?
Yeah, exactly. Whenever, like, as soon as the satellite galaxies merges with the host galaxy, the black holes merges. So if you want to study the dual agents, those would be caused by black holes, stalls by a parsec.
So you're just going to go sort of after the merger, you get a kick that's not so strong a kick as you actually get inducted.
Yeah, the black holes would be back and forth.
Yeah, so that would be something we could look at in terms of
Yeah, the base side, yeah, so a fraction of the black holes that have to be displayed because the big velocity might not be enough to eject the black hole, but it could be enough to make the black hole fall, I think.
compare that to now, right?
No,
But they can design special sharp.
yeah, the time scale.
Any other questions? Let's thank